and thank you for tuning in. Welcome to a new episode of the Passion for Technology podcast by EBV Electronic.
Welcome to the Passion for Technology podcast. The EU Energy Efficiency Directive mandates energy efficiency improvements within the European Union. On October 10, 2023, new EU legislation in the context of the Energy Efficiency Directive aimed at achieving a sustainable energy economy came into effect. A new binding target for reducing energy consumption was also issued. By 2030, energy consumption is to be reduced by another 11.7% compared to the previous target. This means that instead of the previously targeted 846 million metric tons, only 763 million metric tons of oil-equivalent final energy are to be consumed. Electricity plays a key role in sustainable development. On one hand, a large proportion of the primary energy used is lost to conversion. And on the other hand, new application technologies, for example, e-mobility or heat pumps, lead to increased electricity consumption. In this context, a semiconductor material is increasingly coming into focus: silicon carbide or SiC. Today, we will be talking about why this material is so exciting and where it offers opportunities in terms of sustainable power generation and use. Our guests today are Milan Ivkovic, Director Segment Analog and Power at EBV Electronic, and Milan is a returning guest who has been twice on the show already. Hi, Milan.
Hello.
And Hunter Freeberg, Technical Marketing Engineer at the Power Solutions Group at onsemi. Hi, Hunter.
Hello, hello.
Hunter, why is SiC so exciting in terms of sustainability?
So it's for a couple of reasons. First and foremost, power efficiency. It's a more efficient technology than silicon at higher power levels. And I believe we'll touch on that shortly. But then in addition to that, the systems that utilize silicon carbide have the benefit of utilizing less raw materials. So smaller passives like inductors and capacitors, and smaller heat sinks for dissipating heat away from systems.
You just mentioned efficiency, Hunter. Are there any values for how much energy can be saved by SiC power elements?
So I'll give you a couple of examples. When you talk about next generation high power designs, EV charging is one of the large applications. And some of those applications within EV charging, the very high power levels, you're talking like 100 kilowatt superchargers. There's a lot of power savings to be had there and a lot of power dissipation in those applications. So to a silicon carbide based design, you may see a couple percent efficiency increase. For instance, onsemi has some onboard chargers, a different application, where you see a 2 to 3% increase moving from a silicon to a silicon carbide based design. Doesn't sound like a whole lot. But again, when you talk about these 100 kilowatt chargers and even next generation 1 megawatt chargers, even at a 1% efficiency increase for a 100 kilowatt charger, that's 1 kilowatt. So that would be the equivalent of like leaving a small burner on your stove, on your electric range. Or another example would be like a common LED light bulb that's used to replace a standard 100 watt incandescent. It's about 5 watts. So that'd be the equivalent of about 200 LED light bulbs. So there's a lot of power savings that can be had by adopting silicon carbide in these next generation applications that utilize a lot of power.
That helps, Hunter. That helps to picture and translate what energy efficiency actually looks like in reality. And you also touched up on a couple of applications. Milan, could you elaborate a little more on potential applications? Where is this particularly interesting?
Yeah, as Hunter already indicated, in general, any application that is benefiting from higher efficiency or higher energy density into processing power. And we already have a couple of applications that became a mainstream for silicon carbide. When talking about electric vehicles, for example, onboard chargers, that was already mentioned, because we need a really smaller device and a lightweight device that is running with our car all along the way. Then traction inverters for high-end passenger vehicles. Here, really, the key is energy density at motor inverters and really limited space and limited ability to remove the heat from the place where inverter is placed. And then obviously EV chargers to support all the infrastructure for electric vehicles. On the other hand, in higher power range, different applications in energy infrastructure like solar or energy storage or UPS. This is already today what we see that is benefiting from silicon carbide benefits.
Hunter, anything that comes to your mind there? Any additional applications?
Well, I guess I'd kind of piggyback off of the traction inverter example, for instance. So the applications really boil down to power supplies and motor drives. It's all power conversion. An industrial motor drive would be the analog on the industrial side of things to a traction inverter. Like Milan said, that's the motor drive that goes into your car. Whereas with an industrial drive, maybe that goes into an HVAC system, into industrial robotics, into heat pumps. So with adopting silicon carbide into those applications, you can potentially have much smaller systems and smaller drives.
So these are all areas where high power is required. Milan, what are the minimum power levels where SiC can be utilized? What's the other direction look like?
Yeah, so obviously there is a minimum power level because here the target with silicon carbide is really to touch higher power conversion. And there should be some limit, which is actually commercially set, we can say, where below that doesn't make so much sense. So where we see the lower limit is several kilowatts, or let's name it like applications that are operating from single phase power supply if you go in this direction. So then we typically say like 1 kilowatt, let's say. It's not something like set in stone, but this is where you start with the silicon carbide. And on the other end, for sure, like limit is very high because you can have a device that is processing like 50 kilowatt of power. But if you parallel or stack, then you go much higher.
More power usually also means higher voltages. Hunter, what's the trajectory of this development?
So the existing technologies really are in the range of 650 volts up to a couple of kilovolts. One example would be, for instance, for utilizing switches of that voltage would be like a single phase input into your home. And if you have any kind of industrial charger or like an onboard charger in your car that utilizes that single phase input, that's typically where you'd see the 650 volt switches used. But if you're going to even higher power level, like a 3-phase input, for instance, 400 volt AC like you see in Europe, typically 1200 volt switches will be used in those applications.
Yeah, and I would add on the top of that there is a trend in solar to go to 1500 volt DC bus. So definitely this is to be supported with the 2 kilovolt plus devices. And we also see need of customer in the direction of static transformers, where really the device can operate in 10 kilovolt range. And then devices that can support it are really, let's say, more than welcome.
What does this mean for power electronics and the use of silicon carbide?
Yeah, so it means that with the new technology, with silicon carbide technology, with the devices that can withstand high blocking voltages, which are efficient in terms of conductive losses and switching losses, now this is enabling some new topologies that were not usable, I would say, with the silicon IGBTs. And just to give example, with the 1200 volt devices, we can address a bunch of applications with 2-level topologies now. And also to come to lower end of power with silicon carbide, for example, you can design a totem pole in a PFC stage. With silicon was like you had to do some tricks around.
Diving a little deeper, Hunter, how exactly does the use of silicon carbide semiconductor devices improve energy efficiency?
So silicon carbide improves energy efficiency, mostly when you compare the material properties, again, between silicon and silicon carbide. There's 3 key properties that I'll highlight, that being the higher breakdown voltage, the higher saturated electron velocity, and the higher thermal conductivity of silicon carbide as compared to silicon. So it's called a wide bandgap material. If you're not familiar with what exactly that means, basically that means that the device or silicon carbide acts more like an insulator than it does a conductor as compared to silicon. So what that results in is we can develop an epitaxial layer when you fabricate the devices that's much, much thinner. It's about 90% reduced thickness compared to silicon. So the structure of the FET the way that the current flows through the FET is vertical in nature. It's top down. So when the charges are having to fight through less material, one, they are far less resistance, which improves their energy efficiency. And again, you can develop much higher voltage devices. Again, 650, 1200 volt, 1700 volt, 2 kV and up. So again, the other parameter, the saturated electron velocity, basically all that means is that the charges move through the silicon carbide material faster than they move through silicon material. So it's about 2 times higher with silicon carbide as opposed to silicon. So that means that your switching frequency can be quite a bit higher with silicon carbide as opposed to silicon. And what that means basically is that as your switching frequency increases, then the size of your passives, like your magnetics, like your transformers, your boost inductors, and other passives like your capacitors, they get smaller. So when we mentioned at the beginning, the reduction in raw material that's needed in silicon carbide designs, that's one of the examples, for instance, again, is the reducing in the size of those magnetics and those passives from the higher switching frequency that silicon carbide is capable of. And then lastly, the thermal conductivity of silicon carbide is about 3 times higher than silicon. So basically what that means is that you can sink heat away from a system much faster. So where you previously may have needed more complex cooling systems with a silicon-based design, like having a water-cooled system, you could now potentially just move to a standard forced convection system with a copper or aluminum heatsink. And then if you may have previously had just a very large heatsink and a fan to cool said system, you could move to a much smaller heatsink. So it's really those 3 key parameters, material properties, that make silicon carbide preferable to silicon in high power applications.
So given these properties, Milan, in which types of devices or components is silicon carbide being used? Will it, for instance, completely replace the classic silicon power components?
Yeah, so good news for silicon components. There will be still place for them. But the main target for silicon carbide should be power horse of power electronics. This is IGBT and silicon diode. So what is already today in 1200 volt voltage classes and 650 silicon carbide is there, no doubt. And we see development of more and more higher power and higher voltage modules. So definitely IGBTs. And also on 650 volts voltage level super junctions in some lower power applications. And lastly, maybe worth to mention each system needs auxiliary power to supply processors and so on. So with the 1700 volts, for example, silicon carbide, we can have a new life for flyback with a single switch, right? Where really not highest efficiency is needed. So this is also a place where we see silicon carbide is taking place and replacing some cascode connections or different configuration of flyback.
In terms of cost, are power electronics based on SiC more expensive than past solutions? What's your thinking, Hunter?
So device for device, silicon carbide is more expensive if you're just comparing the discretes, or I suppose the modules. But one-to-one, yes, silicon carbide for now is more expensive. However, what we like to mention to customers and those doing development of these next generation high power systems is that benefit of silicon carbide of being able to reduce the size of those expensive components, those magnetics like your transformers and your inductors, those are very, very expensive components. So when you look at the system level, it may be a wash, more or less. It may be equivalent from silicon carbide to a silicon design. So while the individual switches may be more expensive, the overall system cost due to the reduced size of the magnetics and the reduced complexity that may be needed to cool that system results in a cheaper system. So it's not as much of a cost increase as you may think with silicon carbide.
Milan, what does the use of SiC mean for the design of power electronics? We touched on various aspects, but what other dimensions and perspectives are there?
Yeah, so this is different technology than silicon. And then even that there is a, let's say, same functionality, we can say when it comes to really putting silicon carbide into circuit, there are different considerations from the designers that has to be taken. So for sure, this is a device that is different for driving. Driver has to be adopted to silicon carbide voltage levels. enough current to be provided to switch to turn on and safely turn off. And also isolation, because now these devices are going to switch very fast. So common mode transient immunity of the gate driver is one also of the key parameters. And as a, let's say, guidance, it's not that just you take silicon carbide and make drop-in replacement to IGBT. Technologies are developing towards devices that are easier to drive, but definitely there are a lot of considerations from a designer to take care.
Hunter, if there's anything you'd like to add, this is your chance.
One additional thing that I might add that eases the considerations a designer may make in opting for silicon versus silicon carbide is simulation tools. And onsemi, for instance, has fantastic simulation tools between the self-service Plex model generator, which is a very accurate thermal and electrical simulation model generator, as well as the Elite Power Simulator that uses those models to test the device level efficiency and system level efficiency of silicon carbide based designs with a number of different topologies. So if customers or a designer is really on the fence of whether they're going to utilize silicon carbide, utilizing these simulation tools is a good step in the right direction.
Into what direction is the development of SiC power electronics heading? What do you, and I mean both of you, see in the future for SiC power electronics? Hunter, why don't you start? And Milan, I'd also love to hear what you think in terms of what the future holds.
Yeah. So silicon carbide, ultimately, the entire semiconductor industry in general, it's predicated on improving performance and cost. So our expectations with silicon carbide, it's still in its infancy in a way. The technology hasn't at least been around as long as silicon, or at least been in development as long. So while it sees further adoption and further investment into improving yields, into improving capacity, into improving quality and reliability in manufacturing, you'll see the performance increase and the cost decrease.
Yeah, I can add from my side that exactly as we will see that price is decreasing of silicon carbide, and also it becomes more mature technology, this will be motivation for more and more designers to use it in different applications. So I definitely think that we will see much larger adoption of silicon carbide. And also it will mean that a lot of engineers that were not dealing with it previously will have now a challenge to adopt the new technology. And we are together here to help everyone, to help adopt silicon carbide. So then just my message to the audience would be, please contact EBV and onsemi to help you in your new designs for silicon carbide.
Thank you both. I find these wide band gap materials and all the properties that they have and what they enable to do very, very interesting. And this was a beautiful and highly interesting deep dive into silicon carbide. Now, Milan, since you're a returning guest, you know what I'm about to do. And that is, our podcast series is dubbed Passion for Technology for good reason. And I'd love to know when and how both of you developed your individual passion for technology. And Milan, I'll give you another couple of minutes to think about I think this is your third time on the podcast, to think about yet another anecdote from your past life and the origins of your passion for technology. But Hunter, what about you? You go first and you help us and our listeners hear and understand where your passion for technology originates from.
So from my side, I've been passionate about hardware and electronics for a really long time, all the way back to being 10 years old, building computers as a very young kid. And then in deciding what I wanted to do with my life, I always kind of knew that I wanted to be involved in the renewable space and have a helping hand in trying to change the world. So my background is a double E in semiconductor manufacturing and device physics. So naturally, I kind of gravitated towards the semiconductor industry. And again, a passion for renewables, young, bright kid wanting to change the world, just excited about the space.
That sounds just beautiful. So you seem to have found the right path to the right place for doing what you've had in mind. And Milan, how about yourself? What's yet another anecdote from your life?
Yeah, Mustafa, thanks for giving me some time to think about it. And I have to be consistent in what I'm telling. So definitely still problem solving is something that motivates me, and how this problem solving is, let's say, making our life easier. But my recent, let's say, experience and what is bringing more passion for power electronics is like I had opportunities really to drive several electric cars, and I had really possibility to feel how this is enabled by technology, right? And we are humans at the end. We can talk about sustainability and so on. We have to understand this. But when we are talking about raw power interaction, we can really feel. So this boosted my passion for power stuff. And also it was very cheap. So it was boosted even more.
Awesome. Well, thank you, Milan, and thank you, Hunter, for the insights that you've shared with us and our listeners today. Dear listeners, as always, you can find more info in our show notes. Please feel free to subscribe to our podcast, Passion for Technology, on either Spotify, Apple Podcasts, or any of the other popular podcasting platforms. Milan, Hunter, thank you for joining us today.
Thank you.
Thanks for having me.